So in this example, they say hydrogen iodide is formed during a reversible reaction when hydrogen and iodine react at 424.5 degrees Celsius. Initially, there is 1.2 mole of hydrogen, 0.9 mole of iodine, and 1.9 mole of hydrogen iodide in a closed container of 2 cubic decimeters. At equilibrium, it was found that there was 0.12 mole of iodine left. Calculate Kc. Now, it's very important here to note that we have not been given the chemical equation of this reaction. So you have to write it and balance it. So to ensure that it is balanced, you'll see that on the left hand side you've got iodine, right? 2 atoms of iodine, 2 atoms of hydrogen, and on this side, on the right hand side, we've got 2 atoms of hydrogen and iodine as well. So the chemical equation is balanced because the number of atoms on the left hand side is equal to the number of atoms on the right hand side. Now, you look at this table, slightly different from the one that we had in the previous example. The difference is in this first column where the descriptors of the different rows are no longer the molar ratios reacted. This is just a different convention that they use. You can see that there's an acronym of RISE here. It's very quick for you to remember that R will stand for the stoichiometric ratios, as you can see them, 1, 1, 2. I will still be initial for the initial moles that are present in the reaction vessel or container. And change will be similar to the moles that have changed. In other words, the moles that have reacted or the moles that have been produced when we're talking about the products. And E will stand for the moles at equilibrium. And then C, this side will be the concentration. But if you remember RISE, you will know that the row that follows RISE will be the row for concentration of your chemical species at equilibrium. So, quickly, let's continue. We are told that at equilibrium we are left with only 0.12. So the moles that have reacted will be the difference between what you started with and what you are left with, and that will be 0.9 minus 0.12, which will give you 0.78. So it means that you changed by 0.78. You reacted 0.78. You started with 0.9 and you minus 0.78 to create 0.12. So, and then on this side, if you use the stoichiometric ratio 1:1, you react 1 mole of iodine with 1 mole of hydrogen. If you react 0.78, you'll also react 0.78 here because of the 1:1 stoichiometric ratio. And now, if you react 1 mole of hydrogen to form 2 moles of hydrogen iodide, how many moles of hydrogen iodide will you form if you react 0.78 of hydrogen or iodine? So it's 1:2, and then you have 0.78 is to x. 0.78 is to x. So if you do a cross multiplication, your x will be equal to 1.56 mole. 1.56 mole. So this will be plus 1.56 mole. You might be asking yourself a question to say, why are we putting minus this side and not this side? Because if you look at our reactants, you started with 0.9 and you ended up with 0.12. It means that the equilibrium shifts to the right. You have reduced the number of moles of your reactants that you had, and you have made more of your products. Sometimes the equilibrium can lie to the left, especially if you are given the initial moles of your product. It can lie either way. You have to use your discretion. You have to look at what you are given at equilibrium and try to understand if you started with a reactant of 0.9 and all of a sudden you end up with 2 point something here at equilibrium, definitely you will know that the equilibrium lies or shifts to the left, because I mean this will be your product this side. You can't start with something then react and then end up with something more. You have to reduce it. So by looking at 0.12, it told us that we are actually we are at equilibrium. We've reduced the amount of reactants that we started with. Okay, but if you start with 0 here, as in the previous example, it will always shift to the right. You'll know that your equilibrium shifts to the right, because there's no way you can react 0 moles of something to form something else. So this one is a given. It will always shift to the right. So that's one thing that you need to take stock of. You need to take inventory of the fact that sometimes the equilibrium will shift to the left, sometimes it will shift to the right, especially if you've been given the number of moles of the product. So you have to use your arithmetic knowledge to make sense of that. Anyway, so let's continue. So here you have 0.78, so you have 1.2 minus 0.78. So top of my head, this is going to be 0.42. You can use a calculator to just confirm it. 1.9 plus 1.56 will give us if you take 5 here, you left with 4, you have 46, so this will give us 3.46 at equilibrium. So as you can see, the equilibrium shifts to the right as our assumption. So you have made more of your products than you started with. So the concentration at equilibrium will be 0.12 divided by 2, which is 0.06. And here you'll have 0.42 divided by 2, which is 0.21. And here you'll have 3.46 divided by 2, 3.46 divided by 2, which will give us 1.73. 1.73. That should be the right answer. Anyway, so you come here, this will be your equilibrium expression. You have your squared here because of the 2 here, and you've got your 1 here because of the coefficient of the stoichiometries that are 1. So you substitute your concentrations. Your product is 1.73 squared divided by iodine is 0.06, 0.21. This one I'm gonna need a calculator. Then the answer becomes let me use a different column to write the answer. The answer becomes 237.53. You can use a calculator to just confirm it, and that's it.